without any further ado, we are going to begin today's seminar. Our first speaker is actually one of our students, a PhD candidate. She's Aniseh. Aniseh, can you hear us, right?
Yes, I can hear you.
Okay, perfect. So his presentation is going to be about developing appropriate commingled mixtures of tailings and waste rocks and assessment of the physical and chemical stability of materials. So conventional practice for the disposal of surface mine waste has developed in serious geo-environmental issues. Tailings are the byproducts of mineral extraction for almost all mining operation, usually transported hydraulically as slurry and stored behind dams. These dams, which are often constructed from a coarse fraction of the tailing material, can cause serious problems, such as the poor stability of the tailing in toilet and difficult inland reclamation. Also, tailing contains sulfide minerals, are prone to oxidation and acid rock drainage, ARD, generating upper exposure to oxygen and water. The second waste stream of surface mining operation is the waste rock, which is conventionally handled to waste dumps. These dumps cause geochemical stability problems or are prone to ARD generation because of their porous structure, allowing oxygen and water to follow through them. The recurrence of the issues mentioned above has encouraged the industry to seek an alternative approach to segregate disposal methods in an attempt to minimize and, if possible, avoid them. To that end, an engineered commingled mixture of waste rocks and tailing is proposed to be deposited in self-supporting dry stock. The commingled mixture could address the conventional disposal drawbacks by benefiting from both waste stream desirable properties. This research investigates the physical and chemical characterization of the mixture, which depends on the properties of its constitutive materials and the mixture ratio. In this study, the geotechnical and geochemical properties of the material with several different mixture ratios are investigated using column permeability tests and computerized axial tomography, CAT, scan imaging. This research aims to better understand and predict the commingled material performance. So with that, just join me in welcoming Aniseh.
Thank you, Daniel, for introduction. Good afternoon, everyone. I'm gonna start my presentation by the environmental impact of mining. To understand the environmental impact of mining, we need to know the amount of land used for the mining project. For mineral extraction, the area used is more than 57,000 square kilometers. Geotechnical and geochemical stability of mine-based stream are the main environmental challenges in mining industry. The first waste stream is waste rock, which is the low-grade host rock that needs to be excavated to reach the ore. The waste rock is usually hauled and emptied to the waste rock stockpiles, and this method of construction caused segregation of large cobble to boulder-sized particles rolling down to the toe and coarse and fine layers at the angle of repose over that base rubble zone. In general, waste rock geotechnical stability is high for many reasons, like high strength, low drainage, low saturation, low density, and low compressibility of waste rock. On the other hand, the geochemical stability of waste rock is low because of internal structure of these piles. Because of segregation, these dumps can generate acid rock drainage when it is exposed to oxygen and water. Oxygen supply is from the base of the dump through advective flow in the rubble zone. Over the rubble zone, there are coarse and fine layers at the angle of repose. The coarse rock and gravel, the coarse layers, which is rock and gravel, remain fully drained and unsaturated, and it provides pathway for upward flow. The fine layer remains saturated, and it provides flow path for the water that infiltrates the dump surface. So these structures develop a reactor to oxidize waste rock piles. The second waste stream is tailings, which is the byproduct of mineral extraction process. Tailings usually have large volume of processed water and transported as a slurry to tailings impoundments. During a slurry deposition, particle segregation occurs, which forms a beach of coarse particles near the discharge point, and fine particles transported by water toward the distant pond. So tailings have a high water content with an initially low in-situ density and low mechanical strength, which makes these structures prone to liquefaction. In terms of geochemical stability, tailings are typically saturated with high water content, which leads to low diffusion coefficient, and low diffusion makes tailings chemically more stable than waste rock piles, since oxygen flow is very limited. However, unsaturated tailings in sand embankment and beach sediments are free to oxidize and generate acid rock drainage when it is exposed to oxygen. The commingled mixture of waste rock and tailing is an integrated approach that can potentially reduce or eliminate the environmental challenges regarding the segregated disposal. If we mix these two wastes together, first of all, less volume of land is required because tailings can be stored in the void space of the waste rock. And if the air voids in the waste rock are filled with tailings, the shear strength of the mixture will increase when the coarse particles are stay in contact. Also, for chemical stability, the voids in the mixture provides a tortuous path for air and water under gravity flow, and oxygen transport by advection would be eliminated for this mixture. And the only oxygen supply would be oxygen diffusion. In addition, this material can be deposited in a dry stack, so we can reduce the cost of building and maintenance of tailings dams. As I said, tailings and waste rock have very different properties. So the behavior of commingled mixture is dependent on mixture ratio of the parent material. In this study, I used particle packing theory for binary mixture, which suggests that the fine waste fill the void space of the coarse particle for ideal mixture ratio. We call this condition just fill condition, the condition that all the voids just filled with finer material. The just fill condition shows minimum porosity for the mixture. As you can see in the graph, other than porosity of parent material, the mixture ratio and particle size ratio significantly affects the porosity of the mixture. In this figure, it is assumed that the porosity of parent material is 0.4. I use the equation in the bottom right from particle packing theory to find the saturation percentage of my mixture, which is based on the porosity and specific gravity of my parent material. There are some critical questions that this research is going to answer. First of all, we want to know if mixing the waste rock and tailings affects the generation of acid rock drainage, and if the mixture ratio of them affects the acid generation potential. We also want to know if the structure and void space of the commingled material can be visualized and quantified. For the mixture of waste rock and tailings, we want to design a mixture and then interpret the behavior based on particle structure. To design for commingled mixture, there are different mixture design variables. But from practical point of view, we cannot change the particle size distribution and shape of the parent material because it's not economical. So we can only alter the mixture ratio of waste rock to tailings and initial solid content of tailings. On the right, you can see different mixture configurations that first introduced by Ben Wicklund. Also, you can see the mixture that I built for each configuration, from waste rock to tailings, waste rock only to tailings only. I calculated the just built condition using the equation I showed you in the previous slide, based on porosity and a specific gravity of a parent material. The ideal mixture ratio for the material I was working was 3.8 waste rock to 1 tailing for the just built condition. As you can see, for this condition, the material has enough cohesion to make a ball with it. The other conditions represent the partially filled condition, which is 2.8 waste rock to tailing, and floating condition, which is 4.5 to 1 waste rock to tailing. As you can see, the porosity increases before saturation point or just filled condition because waste rock void spaces are partially filled with tailings, and the system has air voids. Also, after the saturation point, the porosity is increased again because the extra amount of tailings would separate the waste rock particle and waste rock would float in the tailings. There are limited studies that quantify the effect of mixture ratio of waste rock to tailing on water quality. To understand the effect of mixture ratio on acid generation potential, I ran 5 column tests at UCAT in Rouen, Uganda to investigate the geochemical behavior of different mixtures of tailings and waste rock. There are 2 control columns of tailings and waste rock and 3 columns of different mixture ratios. When we were building the columns, we applied 1 meter of suction below the columns to simulate the water level in the field. In typical condition in the field, the phreatic surface is 1 meter below the surface, and the minus 10 kPa creates unsaturated condition in the material, and it allows investigating the geochemical behavior of the mixture under the unsaturated condition. Our columns were instrumented to measure oxygen consumption rate, oxygen flux, volumetric water content, and substance. There were monthly cycle of wetting and drying. We added 10 liters of water to the waste rock and mixture columns, the big one, and 2 liters of water to the tailings column to replicate field condition in the humid climate. Also, we use the water recovered from the columns to measure the acidity and concentration of different elements. Here you can see the particle size distribution and basic physical properties of parent material. As I said before, the porosity and specific gravity used to calculate ideal mixture ratio. Tailings were consolidated during transportation and storage, so our solid content was so high. We added water to keep the solid content at 75%, which replicate the paste tailings. The tailings we used in this study was from 2 different sources: Canadian Malartic, which is a low sulfide content mine tailings, and also Lagon tailing, which is a high sulfide content one. We needed the sulfur percentage to be about 6 to 7% to make sure acid will generate during the course of the test. So we mixed the tailings together to achieve the amount of sulfur we needed for the design experiment and to accelerate the geochemical response. In the middle graph, you can see the pH of parent material during the test. As you can see, tailings control column were acidic, and the pH for this column were below neutral after about 300 days and below 5 about 350 days. Also, when the pH drops, you can see the concentration of minerals in the tailings column increased in the water collected from the sample. These graphs show the evolution of volumetric water content for commingled columns, the columns with 3 different mixture ratios. Sensors were at 10, 25, and 40 centimeters from base of the column. Each peak shows a start of each cycle when we added water, and volumetric water content decreases as columns are drained. These graphs show favorable conditions for geochemical reactions because of the presence of air during and after drainage. In general, columns showed similar trends, but the column with mixture ratio of 2.8 waste rock to 1 tailings had higher volumetric water content because this column had more tailings and retained more water. These are some of the results of the water quality test for the mixture columns. As you can see here, under forced suction, it took 400 to 500 days for mixture material to get the pH down to 7. If you remember, tailing control column became acidic after about 300 days. The ideal mixture ratio and partially filled conditions shown in blue and orange in the graph, it took about 450 days to reach a pH below 5. It took even more for the mixture of 2.8 to 1 to reach the pH below 5 because this mixture had more tailing, and more tailings means more calcium and sulfur, which is more oxidation and neutralization potential. Also, for this mixture with more tailing, water content is higher, which leads to low diffusion, which makes this mixture more stable chemically, which is because this mixture limits the oxygen flow. To investigate the porosity and internal mixture structure, I use CAD scanning technique. As we all know, X-ray radiation experience attenuation as it passes through the material. We can visualize and quantify the internal structure because of different attenuation between pores and solids. For the first round of experiment, I built the mixture ratio similar to my columns, and you can see they had different internal structure for different mixtures. We wanted to see how tailings fill the void spaces because oxygen diffusion is very limited as saturation goes above 85%, and it can reduce the acid generation potential. Also, for geotechnical stability, we know that the shear strength is higher if rock particles stay in contact. In conclusion, we want to understand the geotechnical and geochemical behavior of waste rock and tailing mixtures. We use column tests to evaluate the hydrogeological and geochemical response of the mixture. The results reinforce the hypothesis that commingled material has a significant influence on ARD generation potential. We also use CAD scanning technique to investigate the internal structure of the mixture. And our goal is to provide recommendation on how to optimize the mixture design and predict the performance of the mixture. Thank you for listening, and I'll be happy to answer any questions.
Hey, thank you very much. Now we have time for the questions. So if everyone here in the room has any question, please raise your hand and wait for me with the mic. Okay, on my way. Now.
Hi, I have a question for you when you're eventually going to try to provide some guidance of how we can provide some recommendations for to do tailings and rock mixtures. How do you think the mixture that you build, you have to study can be applied in the field? It's a mechanical mixture that we think should be put in the field, or the rock waste can be dumped on top of the tailings. Anyway, just to see if we can share some of the ideas with that.
Can you repeat the question? I was hearing the sound very far and I couldn't hear that.
I was just to see if you can share your ideas of how you think you're going to provide some recommendations for field deployment, how to mix rocks, waste with tailings. I don't know if eventually you're going to provide a little bit more some recommendations. And by the way, I like your work. Just I want to see how this scales to the field. Are you going to mix the rocks with the tailings, or are you going to dump the rocks on top of the tailings, or is it going to be a mechanical mixture between tailings and rocks? How do you? What is your vision of how you?
I'm having trouble hearing the question for Aniseh. Are you speaking somewhere in the room, or do you have a microphone?
Yeah, we have
Hi. Can you hear me better now?
Yeah, that's better.
Oh yeah, so I was using the microphone and just to get the speakers to the microphone. So I was just curious about the. At first, I did say I liked the presentation; it was fantastic, great work. But I was curious of if you could share some of your ideas of how this field deployment of rock and tailings mixtures will occur. It's going to be a truck dumping the rocks on top of the tailings. There's going to be mechanical mixtures that could represent some of the findings that you have here. I was curious of how you see industry or I guess an upscaling or pilot phase, how people will do this.
Thank you for your question. For the lab test, we use mechanical mixtures to mix the tailings and waste rock. We measure the dry solid waste and then mix them together using mechanical mixture. I'm not sure how it can be upscaled to the field condition. And how industry can mix these two together for the homogeneous mixture.
Yeah. Aniseh, I can help with that answer. You wouldn't have been studying that component, but I would be happy to offer a short answer.
Thank you.
Yeah, it's actually very simple. Conventional tailing and rock the tailings are discharged by slurry in a pipeline at a high water content so they can pump them. In the case of rock, as Aniseh pointed out at the start of her presentation, waste rock dumps are constructed with haul trucks tipping from the top of the slope of the dump, which gives a very poor structure that allows oxygen and water to permeate very quickly into the dump, producing acid drainage. In the case of co-mingling, it's critical that the tailings have to be dewatered and brought to at least a paste consistency, and better yet, a filtered tailings consistency. And we've had a couple of other students, Rolf Burden, looked at mixing filtered tailings at Penasquito with rock. But what no one has showed us, and if for those who went to the PASTE 2023 conference, you would have seen a presentation by Antamina, and they're doing it with conveyors, and it actually works amazingly well. The waste rock, and if you have rather than using haul trucks to move the waste rock, it's done with a big, large conveyor system. And so while the rock is being conveyed, and sometimes it's quite a distance, you simply place the tailings, pour the tailings, or deposit the tailings on the conveyor belt. And it's quite amazing how quickly it mixes as it rides on the belt. And a couple of transfer points, and you get this excellent mixture, as you see right in front of Aniseh. Do they see the thank you that I see? That comes right off a conveyor belt, and it just happens so well and so quickly because the conveyor belt has bogies in it, and the belt rides up and down and vibrates, and then you do a transfer point or two, and it's mixed just as you see in front of Aniseh. So it's a revolutionary way of handling mine waste. No more tailings ponds, no more acid generating waste rock dumps, no more failures, no more. It really is, but it's taking time to get the industry to look at how to do it. So I'm sorry for jumping in on that, Aniseh, but I felt I could help a little bit.
Yeah, thank you so much.
Okay, any other question? Okay.
So Aniseh is already getting job offers. I don't know if I can say that, but I know because they're phoning me, asking about her. So.
Hello? Hello, can you hear?
Yep.
Oh, okay, good. Yeah, I get two questions. One is, can you go back to your second or third slide about the PSD, the particle size distribution? I want to have more sense about what is your waste rock looks like? Is it like a gravel? And then for your tailing, are you talking about MFT?
Are you asking about the waste rock or tailings?
Yeah, that's another question. It's very good. This is hard rock mining that Aniseh is looking at right now. So there's boulders. There's some of the rocks are the size of footballs and bigger, and the tailings are in many cases gold and copper mines. They've tried it in the oil sands, and it works for oil sands as well. But it's coarse material. It's actually when Aniseh says waste rock, it is truly waste rock.
That means you are mixing a sort of a gravel or even.
You see the particle size on her drawing. It's very large. You can see this. I can't see the scale there, but it's it can be up to.
Okay, yeah, that's fine. Yeah, I just want to get some sense. Yeah.
No, it's an excellent question. It's an excellent question.
But even for the tailings, you are talking about mature fine tailing, MFT, isn't it?
No, in her case, these are gold tailings.
Gold tailings. No sense. Just no sense. Okay. Okay. How about in the last slide, using CT scan to do an analysis on your material? How you perform the CT? Is it like a slurry? You frozen it to do the CT, or how you technically do it?
I cannot hear the question very well. Daniel, could you please repeat the question? I said CT scan and mixing.
Hello? Can you hear? Hello? Can you hear?
Yeah, I can hear you, but from microphone.
Yeah, my question is, how you technically do the CT scanning on your mixture? Do you frozen it or whatever?
No, we don't freeze them. We mix the waste rock and tailing, and we sculpt out the big particles because of the size of the cylinder, and then we mix them, put them in the cylinder in layers, compact them, and then CT them to figure out the porosity and the air content, water content, and the solid content of the mixture.
Any other question here in the room?
Who is asking all the questions? Those were excellent questions, by the way.
Oh, okay.
And I commend you for that.
First question was Professor Gonzalo Zambrano. Second question was Gilbert Wu, right?
Excellent questions. Thank you.
Thank you.
Any other questions here or from the people on Zoom? Yeah, those are chats. Okay. So thank you very much, everyone, for being here, and thank you very much, Aniseh, for this presentation. And yeah, see you next week with other seminar.
Thank you so much.
Thank you.